Alright, this is online class 10 for Statistics Math 125. Today we're going to cover section 6.3, entitled Applications of Normal Distributions. It's Wednesday, October 24th, fall 2012. Alright, this section in our text is entitled Applications of Normal Distributions, and as I hinted in class, I probably would have titled this a little differently if I was writing this book. I would call it Non-Standard Normal Distributions, because that's what it really talks about. The idea of a standard normal distribution is kind of ideal, perhaps in a more practical situation. We're going to be talking about non-standard normal distributions. Alright, I want to recall the last thing we covered in the last online class. When you see this bell-shaped curve, alright, we have symmetry with respect to the mean, and the peak of the bell always happens at the mean. The horizontal axis represents a random variable, which you can call x or y or anything else, and I don't want us to lose sight of the fact that this envelope, this bell-shaped envelope, really indicates a piling up of scores underneath it, or a piling up of x values underneath it. And I'll signify that with these crude little circles here. Alright, we see many of our data points represented by these circles fall within a mathematical neighborhood of the mean. Alright? Not too many of these circles are going to pile up on the extremes. And that's what normal is all about. You don't have too many high values, you don't have too many low values. Most of your data values or scores are piled up in a neighborhood of the mean. The mathematical formula for this bell-shaped curve, now don't panic, I'm going to write it down for you here. It's in your book in section 6.2, and it is an exponential function, and I guess you could claim it's beyond the scope of this course to juggle this formula around. But don't panic, because the calculator and the tables accompanying us, our book and the appendix of the book, handle this formula for us. So I just want to, for formality's sake, cite the formula from which this curve emerges. And I do want to point out a couple of things. Let me get another color here. About this formula that you'll notice, see in the pink there, that mu exists in this formula. So mu determines where this bell-shaped curve is going to peak, and of course sigma is your standard deviation, and sigma determines how wide the bell is. Alright, as you know from last time, there's tall, skinny normal distributions. There's short, fat normal distributions. There's distributions that fall somewhere in between. Yeah, well, the idea is we'll be able to handle any non-standard case we desire. Alright, let me go back to yellow here. This is my notation, not the text author's notation. You signify that x, a random variable x, has a normal distribution with this notation. X, a random variable, is normal, and when you say you've got a normal distribution, you want to know two things. You want to know where's the peak and how wide is it, and of course the mu determines where the peak is, and sigma determines how wide it is. So let me write that down. The mu determines the location of the peak of the bell, and your sigma value, your degree of spread, of course, determines the width of the belt. Okay. Alright, so that was kind of a rehash of our last lecture. Let me get a new layer here, and I'm going to start talking about 6.3 in earnest. Alright, here we go. In section 6.2, you recall we were always in the standard normal case. We were given z-scores. And z means a standard normal, right? We could find probabilities. Probabilities with our normal CDF command. Also, we could work this in reverse. If we were given probabilities, typically in terms of percentiles, we could find the z-scores corresponding to those probabilities. And to do that, we use the inverse norm command. All right. Now, again, this was for a standard. Normals. And for standard normals, the mean is always 0 and the standard deviation is always 1. Alright, what about non-standard? What about non-standard normal distributions? Let me give you an example here. And I'm going to say, suppose. I'm going to write a little bit here, make up my own example here. Suppose heights of adult U.S. males are normally distributed. And what does that mean? That means there's not too many really tall people, and there's not too many really short adult U.S. males. Most adult U.S. males center around the mean value. All right? And I'll give you that mean with a mean of 69 inches and a standard deviation of 2.8 inches. Okay? I'll ask this then. Find the probability that a randomly selected U.S. adult male has a height between 67 and 70 inches. Alright? Really, I'm asking here, let me summarize the information I'm given here. I'm going to let x be a random variable that represents all the heights, or all the varying heights of U.S. adult males. I claim that this variable x has a normal distribution, but it's not standard. The mean is 69, and the standard deviation is 2.8, of course, in inches. All right? So we want to find the probability that x is between 67 and 70 inches. All right? remember from 6.2 we used, for the probability that a z variable was between any two limits of interest, we used the Normalcdf command. We're going to use the same command here, but we're going to account for this non-standard case where we've got a different mean and a different standard deviation. Well, use Normalcdf, same function we used last time. Well, the syntax for Normalcdf, as you recall, you plugged in a left bound and a right bound, but there is also two optional entries where you can plug in the mean and standard deviation. So let me put that down. Right. And the reason it worked for our standard case is if none are entered into this command, the TI-83 assumes the standard case. In other words, that the mean is 0 and the standard deviation is 1. But of course here we're in the non-standard case and we've got a different mean and a different standard deviation, so of course we will enter in these values as my optional mean and standard deviation entries. Alright, so for this problem, I'll plug in Normalcdf. The left bound is going to be 67. The right bound is going to be 70. The mean is going to be 69 inches. And the standard deviation is 2.8 inches. Let me make sure you check that. 69 and 2.8. In the left and right bound are 67 and 70 inches. That looks good. Alright, so under the distribution menu, you find this Normalcdf command. Plug in these four parameters, and we punch out a value of 0.40. I'll call it 0.4020, just 0.402. Alright, using this Normalcdf command makes it easy for us, even in the non-standard case. Now, the book doesn't quite use this option here to its full power. I like to use the TI-83 to the full power that we have available to us, since all of us have the TI-83 calculator. Alright, let's do another example. Same scenario. I'll say find the probability that a U.S. adult male has a height, let's say, less than 68 inches. Yeah. And we'll assume the same given information before. In other words, we're going to normal distribution with a mean of 69 and a standard deviation of 2.8 inches. Alright, well, and if I'm in a, let me draw a little bit of a picture here. This represents the distribution of U.S. adult male heights. Follows a bell-shaped distribution. The bell peaks at a mean of 69 inches, and we want the probability that a U.S. adult male has a height less than 68 inches. Well, let me draw 68 inches here, a vertical line under this graph representing a height of 68 inches, and I really want the area under this non-standard normal distribution below 68 inches. Alright? Alright, we work this out in the same way. Remember, this area is the probability that we seek. So I can symbolize it like this. I want the probability where X represents a randomly selected U.S. adult male, the probability that X is less than 68 inches. Alright, well, notice there's no left boundary, or there's no explicit x boundary or left boundary for x here. And in that case, theoretically, we'll assume x can go on to negative infinity. So that is equivalent to this statement here. The probability that x is less than 68 and greater than negative infinity. And again, to do this, we'll use our normal CDF command. We'll plug in our left boundary. Now remember, our author says our best approximation for negative infinity will use a minus 999,999. The right boundary is going to be 68 in inches. Alright, our non-standard mean will be a mean of 69 inches. And our non-standard standard deviation is going to be 2.8 in inches. And I punch this out, and I'll call it 0.36. So roughly a third of adults of U.S. adult males have a height less than 68 inches. Probability 0.36. Okay? Alright, so anytime we're looking for probabilities in this non-standard case, basically we're looking at our normal CDF command. You may ask now, can we do this in reverse, just like we did in section 6.2? Can I find a z-score given a probability? And the answer is yes, of course we can. Let me give you an example. Again, we'll assume, let me erase this. We'll assume the above information is still true, that the U.S. adult male heights, and I'll let an x variable represent all those different U.S. adult male heights, millions and millions of people. I'll say it's normal, with a mean of 69 and a standard deviation of 2.8, of course, in inches, as before, right? I'll say find the U.S. adult male height that separates the bottom 25% from the top 75%. Alright, our author encourages us to draw pictures in this type of scenario. Similar to what we did in section 6.2, but we're in the non-standard normal distribution. Alright, our mean is at 69, right? We have not too many tall people, not too many short people. Most U.S. adult males are somewhere in the neighborhood of 69 inches, 5'9" in height. I want the height that separates the bottom 25% from the top 75%. Well, what I'm going to do is draw a height here. Say I don't know what it is, but I know that the probability of being less than this height is then 0.25, and the probability of being greater than this height is going to be 0.75. Now again, in this scenario in section 6.2, we use the inverse norm command, but again, that was in the standard case. Well, as you might expect, the TI calculator can handle this also. Let me go back and cite that inverse norm command. In the standard case, we always put the area to the left. And that's the way the command is defined on the calculator, and in many of the optional tables and computer programs that we can use. Alright. As you might expect, we can optionally plug in a mean and standard deviation for non-standard cases. As before, if none are entered, The TI-83 assumes a standard normal. The mean is 0, and the standard deviation is 1. Alright? So for this case, of course, we're not in a standard case. We're in the mean is 69 and the standard deviation is 2.8. So if I want this value, I can use the full power of my TI-83 calculator. The area to the left of this desired height is 0.25. So I'll plug in inverse norm 0.25, and we are given that the mean is 69 and the standard deviation is 2.8. Okay. So I'll punch out this value on my calculator, and it turns out 67.11 inches is the value we seek. And that's consistent. If you'll see this value of 67.11, let me get another color here. 67.11 is to the left of 69 on my diagram, so that's consistent. We certainly would expect a value being less than 69 in this example. Okay? Alright. Alright, so that's a third example for today. I want to look at an example in the book, and then we'll call it a day. Let me get a fresh screen here. Alright, I want to look at an exercise in our homework lists. Make sure I got the right number. It's exercise 31 on page 274. Go back to yellow here. And I'm having trouble here. There we go. Exercise 31 on page 274. We're going to do parts A and B. So please pause now and familiarize yourself with this problem. It's a little wordy, but it's an interesting example, and so please pause there now and get yourself familiar. Alright. We're talking about lengths of pregnancies. Right, the author tells us lengths of pregnancies are normally distributed with a mean of 268 days and a standard deviation of 15 days. Alright, let me summarize that. Lengths of pregnancies. As we know, some pregnancies are longer than others or shorter than others. It's variable, and I'm going to let the letter X represent the variable lengths of all pregnancies of all adult women of all time. Right? The book claims that pregnancies are normally distributed. What does that mean? Well, that means there's not too many really long ones, there's not too many really short ones. Most pregnancies are somewhere near a mean value of 268 days with a standard deviation of 15 days. All right. Let me draw a little picture of that. I'm going to draw a bell-shaped curve representing that. The horizontal axis here represents all our possible pregnancy lengths in days. Normal distribution means we're going to be piling up near a mean value of 268. So let me indicate that on the graph. Alright, the standard deviation is 15. I won't label that on the graph. It's kind of hard to visually interpret that. I just know that we'll use that 15 to determine the width of our bell here. Alright, the problem states, one classical use of the normal distribution is inspired by a letter to Dear Abby in which a wife claimed to have given birth 308 days after a brief visit from her husband who was serving in the Navy. Given this information, Find the probability of a pregnancy lasting 308 days or longer. Alright, so 308 days, well, it puts me above the mean. Let me erase that. 308 days puts me up here somewhere to the right of the mean of 268. And if I want the probability that a pregnancy is more than this value, I want the area under this normal curve to the right of 308. This is the area. This area equals the probability that we seek. Okay. All right. So I can symbolize that as before. And again, you may say, well, how am I going to use my Normalcdf command because I don't have a left boundary of interest? Well, remember, theoretically, these x values go off to infinity, and technically I can rewrite this statement. This is the probability I seek. I can rewrite it in this fashion. In other words, the probability that the x is less than infinity and greater than 308. Again, of course, I'll use my Normalcdf command with 999,999 as my best approximation for positive infinity. Alright, so the syntax of your Normalcdf command is your left boundary, your right boundary, and again our author asks us to use 999,999 for approximating positive infinity, and we'll plug in our mean, because we're in the non-standard case, and our standard deviation. Alright, so if I punch that out on my calculator, I get a value of 0.0038. Alright, now 0.0038, that's approximately 0.004. And 0.004 really means 4 over 1,000, 4 1,000ths. So what this is telling me is about 4 in 1,000 pregnancies will last 308 days or more. And that's a rare event. Alright, so the book asks us what could we conclude about this. Well, remember, this all started out because a woman had a child 308 days after a visit from her husband in the service. You can conclude one of two things. Either a rare event has occurred, or the husband is not the father. Alright. Let's look at part B now to the same problem. So the same given information. Read the part B. If we stipulate that a baby is premature, if the length of pregnancy is in the lowest 4%, find the length that separates premature babies from those who are not premature. Alright. So basically we want the probability of getting a premature baby here. Let me draw the distribution. Always helps to draw a distribution. Draw a little picture, bell-shaped distribution of what's going on in this problem. We're in the non-standard case with a mean of 268 days regarding these pregnancies. Now I want the probability, or let's see, if, we read that first sentence, if we stipulate that a baby is premature, if the length of pregnancy is in the lowest 4%, find the length that separates premature from those who are not premature. So some pregnancies last less than 268 days. The idea here is we need a cutoff. Right, that cutoff will separate the premature from the not premature babies. Now, the author is specifying that a baby is premature if the length of pregnancy is in the lowest 4%. In other words, the probability of being less than this value is going to be 0.04. Okay? So, if I'm given a probability and I want here on an X score, I'm going to use my inverse normal command in the non-standard scenario. So I'll use inverse norm. Let me erase that. I'll do inverse norm. My area to the left of this value is going to be 0.04. And recall, we'll plug in a non-standard mean and a non-standard standard deviation. As I recall, the mean was 268 days, the standard deviation was 15 days. And I punch this out, and I get 241.7. Now this is in days. So there's the cutoff. If a pregnancy lasts then, well, let's say if a pregnancy lasts 242 days or less, we claim it's premature, and the hospital may want to take special steps at that point. Alright, so we've done 5 examples of this Normalcdf command and inverse normal command in the non-standard case. And again, the calculator makes it easy for us. The book goes into details regarding these commands where they don't use the full power of the TI-83 calculator. So you'll see the development in the book may be a little different from the development here. But certainly we end up at the same place in the answers to these problems. Alright, we're hitting the 32-minute point, so I'll call it a day. And please review the folder materials, complete the online exam as usual. And this concludes online lecture 10 for 6.3, Applications of Normal Distribution.